In the oscillation of springs, consider the following conditions and give answers. A. Two identical springs of force constant K, each are connected in parallel. What will be the equivalent spring constant? Let us discuss the solution of A. So we have two identical springs. Okay. Each having spring constant K, and this is a bar. Okay. So this is a bar of negligible, okay, mass. Bar of negligible mass. Now, let E be the extension produced on each spring, okay, when a mass M is attached, okay, as shown in this figure. So we have this. Clear? So what we find, force or weight equals mg, okay, act in this direction, that is in downward direction. So we have force or we have load or we have weight equals mg acting in vertically downward direction. So we have this, and here mass is attached, okay, to the middle, okay. It is attached to the middle of the bar. So we have this. Now what we find in this case is that, so I'm writing over here. So this is extension, okay. Extension produce on each spring. Clear? Now, due to load, okay, or force, or we can write in this way, weight equals mg on the combined spring system, okay, on the combined spring system, that is we have a parallel system, the force on each spring, okay, each spring is F by 2. So we find this. Clear? So what we find in this case is that force on each spring, okay, is half of the load, okay. Clear? Or we can write in this way, force on each spring is F by 2. So we have this. And restoring force So I'm writing in this way. F res equals minus K times E. So we have this, and restoring force on this spring, okay, on this spring is, so let me draw over here, and restoring force on this spring is F restoring equals minus K times E. So we have this. Clear? And we know, okay, external force equals negative of restoring force. So we have this. Clear? So let us take this spring, okay. So what we find is that external force on this spring, okay, or on single spring equals F by 2. So this equals minus, and restoring force is minus KE. So we have F equals 2 times KE. So we have this. Clear? Now, let Kp, okay, be the spring constant, okay. This is a spring constant or equivalent spring constant, okay, constant of the or for the parallel combination, okay, spring constant for the parallel combination. So we have this parallel combination of the two springs. Therefore, or we can simply write in this way, okay. So Kp is what? This is equivalent spring constant, okay. So this is equivalent spring constant. So we have this. Therefore, for equivalent spring, okay, we can write F equals Kp or equivalent spring constant times the extension. So we have this. Let us call it equation 1. And this is equation 2, okay. Now, we find from 1 and 2, okay. From 1 and 2, 2 times Ke equals Kp times E, okay. So this cancels out. Therefore, equivalent spring constant Kp equals 2 times, okay, the spring constant of the single or spring constant of the each spring. So we have this, okay. So we find this. Clear? So we have this. Now, solution of B, okay. What could be the time period of the vibrating spring in the space? We know time period. So we need to find the time period, okay. Time period of mass spring system is T equals twice pi under root m by k, okay. And for parallel mass spring system, okay, we simply write T equals twice pi under root m by kp. So we have this. And since Kp equals 2 times spring constant of each spring, okay? So we have this. Therefore, T equals twice pi under root m by twice k. So this is the time period, okay? So we have this. Next, okay? What is the acceleration of vibrating spring at mean position and extreme position? So let us discuss this, okay? Solution of C. So let me draw the figure once again, okay? So we have this. So this is bar, okay, having negligible mass, and the spring constant is K. So we have this. Now, when mass M is attached, okay, so we get this. So we have this, okay. Is the extension produced in each spring, okay, when mass M is attached to the middle of the bar in this way, okay. So we have this. Clear? So we have this. Now what do you find? After the extension E, the system, that is mass spring system, will be in equilibrium, okay. So figure second, this is figure second, represent the equilibrium position for this combination, okay. So we have this. Now from the equilibrium position, if the mass spring system is further displaced, okay, so we have this now. So we have this, okay. So let y be the displacement, okay. So we have this. Clear? We have this. So this was for equilibrium position, okay. So we have this. Now what we find is that the mass spring system undergoes simple harmonic motion, okay. So for simple harmonic motion, we find acceleration, okay, A equals minus omega square y. Y is the displacement from the mean position. So this is equilibrium position, or this is the mean position. So we find this. Okay. And what is y? As I said earlier, this is displacement from mean position. So we have this. So this is to be noted, okay. Therefore, at mean position, y equals 0. Okay. Therefore, acceleration equals 0. So we have this. And at extreme, okay, position, at extreme position, let's say this is the extreme position, okay. If this is extreme position, we can write y equals ym. This is the maximum displacement. So at extreme position, acceleration is maximum. So this equals minus omega square ym. So we have this. Clear? So we have maximum acceleration equals minus omega square, and we know omega is twice pi by t. So we can write in this way, twice pi by t whole power 2 times ym, that is displacement from the mean position. And we have time period t equals this, okay. Therefore, we can write A max equals minus 4 pi square ym divided by t square. So we have A max, that is maximum acceleration, equals minus 4 pi square ym divided by t square, okay, square of the time period, and square of the time period gives 4 pi square times m by twice k. So we have this. So on simplification, we get minus 4 pi square ym divided by 4 pi square m, and 2k will move up, okay, to numerator. So this cancels out. Therefore, at extreme position, acceleration is maximum, and A max equals minus 2k ym divided by mass. So this is the required expression for acceleration, okay, at extreme position